There is a question that has been sitting at the center of physics for almost 50 years. And the reason you have never heard it stated clearly is not because it is too complicated for you to understand. It is because the answer, whatever it turns out to be, will break something that cannot be fixed. Either quantum mechanics is wrong, or general relativity is wrong, or reality is not what you think it is. Those are the only three options. And the people whose entire careers depend on those two theories being true have spent half a century trying to find a fourth option that does not exist. Here is the question. When something falls into a black hole and the black hole eventually evaporates, what happens to the information about what fell in? That sounds like a narrow technical question. It is not. It is the most important unsolved problem in fundamental physics, because the answer forces you to choose between two laws that have never been wrong. Quantum mechanics says information cannot be destroyed, not difficult to destroy, not unlikely to be destroyed. Mathematically, structurally, fundamentally impossible to destroy. The entire framework of quantum theory is built on a principle called unitarity, which guarantees that the information describing any physical system is always preserved. Always. You can scramble it, you can scatter it across 1 billion light years, but you can never erase it. The laws of physics run forward and backward with equal validity, and that means the present always contains enough information to reconstruct the past. General relativity says something different. When matter crosses the event horizon of a black hole, it enters a region of space-time from which nothing escapes. Not because the gravity is strong, though it is, but because the geometry of space-time itself curves so severely that all paths, including the path of light, point inward. There is no trajectory that leads back out. The information is not trapped behind a wall. It is trapped behind the structure of space and time. And in 1974, Stephen Hawking proved that black holes are not permanent. They radiate, they shrink, they eventually disappear. And when they do, the radiation they leave behind carries no record of what fell in. None. A black hole made from a collapsed star and a black hole made from a compressed library, if they have the same mass, produce identical radiation. The information about what made them is gone, not hidden, gone. So you have two statements. Information cannot be destroyed, and black holes destroy information. Both are backed by the most rigorously tested mathematics in the history of science, and they cannot both be true. The reason this should unsettle you is not abstract. If information can be destroyed, then the past cannot be reconstructed from the present, even in principle. The laws of physics become irreversible at a fundamental level. Cause and effect become a one-way street. The universe does not merely move forward through time, it forgets. And if the universe can forget, then the entire framework of physics, every equation, every conservation law, every prediction, rests on a foundation that has a hole in it. That is not a metaphor. That is what the math says. In 1984, Leonard Susskind and two colleagues showed that if information is genuinely lost in black holes, the temperature of the quantum vacuum everywhere in the universe should be approximately 10 to the 32 Kelvin. That is 100 billion degrees. The fact that you are not currently on fire is evidence that something in Hawking's argument is wrong, but nobody can find what it is. This problem did not appear last year. It was not discovered by a new telescope or a particle accelerator. It was written down in a paper published in Physical Review D on November 15th, 1976. The title was Breakdown of Predictability in gravitational collapse. The author was Stephen Hawking, and for the first decade after it was published, almost the entire physics community ignored it. Only 8 journal articles in that entire period addressed the question of whether information is lost in black holes. 8. The most profound crisis in theoretical physics since the ultraviolet catastrophe that birthed quantum mechanics. And almost nobody wanted to look at it. That should tell you something about how uncomfortable the implications are. But the story of how this crisis came to exist starts before Hawking. It starts with a 25-year-old graduate student from Mexico City who saw something that every established physicist in the world missed. And when he told them what he found, they told him he was wrong. Every single one of them, including Hawking. Jacob David Bekenstein was born on May 1st, 1947, in Mexico City. His parents were Polish Jews who had met in Mexico during the war. His father was a carpenter. His mother was a homemaker. When Sputnik launched in 1957, 10-year-old Beckenstein gathered with friends after school to build model rockets. He earned his bachelor's and master's degrees from the Polytechnic Institute of Brooklyn, then went to Princeton for his doctorate under John Archibald Wheeler, the man who had coined the term black hole. Wheeler posed a thought experiment that sounds simple and is not. Imagine you have a hot cup of tea. It has entropy, meaning it contains thermodynamic disorder, randomness, information about its molecular arrangement. Now drop it into a black hole. The tea is gone. Its entropy is gone. The total entropy of the universe has decreased. And the second law of thermodynamics, which says entropy never decreases, has been violated. Wheeler put it memorably. If a black hole comes by, I could drop both teacups in and conceal the evidence of my crime. The second law would have no teeth. Anything inconvenient could be disposed of behind an event horizon, and the universe's bookkeeping would never balance. Beckenstein came back months later with his answer. "You have not avoided the entropy increase," he told Wheeler. "You have just put the entropy increase in a new place. The black hole itself has entropy, and that entropy is proportional to the area of its event horizon." He published this in Physical Review D in April 1973. He was 25 years old, and the entire establishment told him he was wrong. Stephen Hawking, together with James Bardeen and Brandon Carter, published a paper that same year explicitly stating that the analogy between black hole mechanics and thermodynamics was just an analogy and not physical. The logic seemed airtight. If a black hole has entropy, then thermodynamics demands it must also have a temperature, and if it has a temperature, it must radiate energy. But nothing escapes a black hole. Therefore, the argument went, Beckenstein's idea is nonsense. Only Wheeler stood behind his student. "Your idea," he said, "is just crazy enough that it might be right." And there is a detail in Beckenstein's formula that almost nobody noticed at the time, a detail that would take 50 years to fully understand. And when it was finally understood, it would suggest something about the nature of reality that is harder to accept than anything the information paradox itself implies. Beckenstein's entropy formula says the information content of a black hole is proportional to the area of its event horizon, not the volume. The area, a two-dimensional surface, encodes everything about a three-dimensional interior. At the time, it looked like a mathematical curiosity. It was not. It was the first clue. But before that clue could be followed, Hawking did something nobody expected. He set out to demolish Beckenstein's idea. And in doing so, he accidentally proved it right. And in proving it right, he created the worst crisis in the history of physics. In 1973, Hawking traveled to Moscow and met two Soviet physicists, Yakov Zeldovich and Alexei Starobinsky. They had been working on an idea called superradiance, which predicted that rotating black holes should fling off particles, bleeding away their rotational energy. Hawking was skeptical. He went back to Cambridge and tried to prove them wrong by applying quantum field theory to the curved space-time around a black hole. What he found instead was something far more radical. It was not just rotating black holes. All black holes radiate. Every single one. The radiation has a perfectly thermal spectrum, like the glow from a hot oven, and its temperature depends only on the black hole's mass. Hawking had discovered that black holes are not black. They shine, and in doing so, he proved Beckenstein right. If black holes radiate thermally, they have a real physical temperature. If they have a temperature, they have entropy. Beckenstein's proposal was not an analogy. It was literal. The proportionality constant that Beckenstein had estimated was fixed exactly by Hawking's calculation. The Beckenstein-Hawking entropy of a black hole is 1/4 of its horizon area, measured in Planck units. One formula containing all four fundamental constants of nature: gravity, quantum mechanics, relativity, thermodynamics, linked in a single equation for the first time. As Hawking later admitted in A Brief History of Time, he had been afraid that if Beckenstein found out about the radiation result, he would use it as further argument to support his ideas about black hole entropy, which Hawking still did not like. So Beckenstein was right, but Beckenstein being right created a problem infinitely worse than Beckenstein being wrong. Because if black holes have temperature, and temperature means they radiate, and radiation means they lose mass, then black holes are not permanent. They evaporate, they shrink, and eventually they disappear entirely. And when a black hole disappears, everything that ever fell into it, every atom, every photon, every quantum state, is now represented only by the thermal radiation it left behind. Radiation that carries no information about what fell in. Radiation that is identical regardless of whether the black hole was made from a star or a grand piano. You need to understand how abnormal this is. Everywhere else in physics, information is preserved. Burn a book. The book is destroyed, but the information is not. In principle, if you captured every photon, every ash particle, every molecule of smoke, every ripple of heat, you could reconstruct the book. The laws of physics guarantee this. The process is extraordinarily difficult in practice, but possible in principle. Quantum mechanics does not merely suggest that information is conserved. It requires it. The mathematical structure of the theory, the unitarity of the S-matrix, is built on it. Remove unitarity and quantum mechanics does not become slightly wrong. It collapses entirely. The probabilities stop adding up to 1. The framework ceases to function. And Hawking's calculation said black holes violate this. A pure quantum state, an object with a definite, complete quantum description, falls into a black hole. The black hole evaporates into thermal radiation, which is a mixed state, a state of maximum ignorance. A pure state has evolved into a mixed state. That is not unitary evolution. That is not supposed to happen. That is not a minor footnote in an obscure subfield. That is the mathematical equivalent of saying that 1 + 1 sometimes equals 3. And Hawking did not flinch from the implication. In his 1976 paper, he wrote it explicitly. Not only does God play dice, but he sometimes confuses us by throwing them where they cannot be seen. The paper was published in Physical Review D, and its implications were enormous. Hawking was not proposing a minor correction to quantum mechanics. He was proposing that the entire structure of quantum theory, the Hilbert space formalism, the unitary S matrix, the deterministic evolution of the wave function, all of it must be replaced by a more general framework that allows pure states to evolve into mixed states. He called this a dollar matrix, as opposed to the S matrix, because, as he joked, it destroys information just as a dollar bill does not last. The joke did not land well with the people who understood the consequences. The reaction from the physics community was, for the most part, silence. A handful of theorists engaged with the problem seriously. Don Page, who was Hawking's own doctoral student at the time, objected almost immediately on the grounds that information loss would violate CPT symmetry, one of the deepest symmetries in physics. But the broader community did not want to touch it. The mathematics was airtight. Hawking was Hawking. And the implications were so severe that most physicists chose to assume the problem would resolve itself somehow, eventually, without requiring them to sacrifice either quantum mechanics or general relativity. It did not resolve itself. It got worse. The numbers involved are important because they tell you something about the scale of this problem that words alone cannot convey. A black hole with the mass of our sun has a Schwarzschild radius of about 2.95 kilometers. Its event horizon has a surface area of approximately 110 million square meters, which is roughly the area of a mid-sized city. Its Beckenstein-Hawking entropy is approximately 10 to the 77th power, measured in units of Boltzmann's constant. That is roughly 100 billion times more than the thermodynamic entropy of the sun itself. In information theoretic terms, a solar mass black hole contains approximately 10 to the 77th bits of information. To put that in perspective, the total number of atoms in the observable universe is estimated at roughly 10 to the 80th power. A single black hole, the mass of the sun, contains an amount of information comparable to the number of atoms in the universe. And the Hawking temperature of this black hole is approximately 62 nanokelvin, 62 billionths of a degree above absolute zero. That is 44 million times colder than the cosmic microwave background radiation that fills the universe at 2.725 Kelvin. Which means that right now, in the current universe, a solar mass black hole absorbs far more energy from the cosmic microwave background than it radiates away. It grows rather than shrinks. It will not begin to evaporate until the universe has expanded and cooled enough for the background temperature to drop below 62 nanokelvin. And once it does begin to evaporate, the process will take approximately 2 times 10 to the 67th years. That is roughly 10 to the 57th times longer than the current age of the universe. The peak wavelength of the radiation is about 160 kilometers, which is not light, not infrared, not microwaves, but radio waves at around 1800 hertz. You would not see a solar mass black hole evaporate. You would hear it if your ears could detect individual radio photons spread across timescales that make the age of the universe look like a blink. These numbers matter because they tell you this is not an academic exercise. The information paradox is not about what happens in some theoretical far future. It is about what the laws of physics say right now. The equations are not speculative. They combine general relativity and quantum field theory, the two most successful theories ever constructed, applied to a physical situation that definitely exists. There are billions of black holes in our galaxy alone. Every single one of them is, at this moment, in a state that our two best theories of reality describe in contradictory terms. The contradiction is not hidden. It is not subtle. It is sitting there in the mathematics, and it has been sitting there since 1976. And the problem is not just that we do not know which theory is wrong. The problem is that we do not even know what kind of thing the answer will look like. This is not a situation where theory A says the electron mass is one value and theory B says it is another, and we just need a better measurement. This is a situation where theory A says a certain process is possible and theory B says the same process is impossible. And both theories have been verified to extraordinary precision in every other context. The conflict is not about numbers. It is about the logical structure of physical law. One of these theories, and possibly both of them, contains a fundamental error that has somehow never shown up in any other experiment or observation. The error is invisible, except at black holes, which are the one physical system where both theories must be applied simultaneously. It is as if you had two maps of the same city, both perfectly accurate everywhere you checked. But when you overlaid them, one of the maps showed a road where the other showed a wall. The maps cannot both be right, but every time you drive somewhere, both maps get you there. The inconsistency only manifests in the one place you have never been. Some physicists have tried to argue that the paradox is not real, that it is an artifact of applying semi-classical physics beyond its domain of validity. But this argument does not survive scrutiny. The contradiction arises not at the singularity, where quantum gravity effects are expected to be strong, but at the event horizon, where curvature can be arbitrarily small. For a black hole, the mass of our galaxy, the curvature at the event horizon is weaker than the curvature at the surface of the Earth. Both general relativity and quantum field theory should work perfectly there. There is no regime problem. There is no hand-waving escape. The theories give contradictory answers in a regime where both claim to be valid. That is what makes this a genuine paradox and not a technical limitation. Now here is something that should bother you. Nearly every explanation of Hawking radiation you have encountered, every YouTube video, every popular science article, every documentary describe the process using a picture of virtual particle pairs popping into existence near the event horizon. One particle falls in, one escapes, and that is Hawking radiation. Hawking himself used this picture in a brief history of time, and it has become the standard way the concept is communicated. And it is wrong, not simplified, wrong. The actual calculation uses a mathematical technique called Bogoliubov transformations. What Hawking showed is that the definition of particle and vacuum depends on the observer. In flat space-time, all observers agree on what a particle is. In the curved space-time near a black hole, they do not. An observer far from the black hole, applying quantum field theory, finds that what they identify as vacuum near the horizon contains particles when translated into their reference frame. There is no local mechanism of particle pairs splitting apart. The radiation is a global property of the quantum field in curved space-time. The virtual particle picture is not even a valid approximation. It is a cartoon that Hawking drew for a general audience, and it has been repeated so many times that most physicists use it as shorthand, even though they know it is misleading. The reason this matters is not pedantic. It matters because the real calculation is what makes the paradox inescapable. The real calculation shows that the radiation is exactly thermal, with no corrections, no subtle correlations, no hidden information. If you use the cartoon, you can imagine the escaping particle carrying some imprint of its partner that fell in. If you use the actual math, you cannot. The thermal spectrum is exact. The information is gone. Think about what information loss really means for you personally. Right now, at this moment, the complete quantum state of every particle in your body is, in principle, encoded in the wave function of the universe. Everything you have ever done, every choice, every thought, every breath has left an imprint on the quantum state of reality. If you could reverse the laws of physics, you could reconstruct your entire history from the present state of the universe. Your past exists, encoded in the present. Information loss says this is not true. If information can be destroyed, then there are facts about the past that are not merely unknown, but that have been erased from reality. Not lost in the way that a forgotten memory is lost, erased in the way that a deleted file is erased when the hard drive is overwritten. The information does not exist anywhere. The past, in some very real sense, never happened. And this is not a question of far future technology. This is a question about the structure of physical law. If a single black hole anywhere in the universe destroys information, then the wave function of the entire universe is no longer a pure state. The contamination spreads. Every quantum system that was ever entangled with the black hole, which eventually means everything in its past light cone, is now described by a mixed state. The purity of the quantum state of the universe, which is supposed to be a mathematical certainty, is compromised. One black hole doing one thing that quantum mechanics says it cannot do is enough to corrupt the entire framework. This is why physicists take the information paradox so seriously. It is not an exotic edge case. It is a stress test on the foundations of all of physics. The philosophical implications are staggering, but the physics implications are worse. If the past is not uniquely encoded in the present, then the present is not uniquely determined by the past. Determinism fails, not the everyday determinism that quantum uncertainty already compromises. A deeper kind. The kind that says the laws of physics are consistent equations that run both forward and backward. If you lose information, those equations develop holes. They stop being well defined. The mathematical structure of physics ceases to be self-consistent. And that is not a hypothetical concern about events trillions of years in the future. It is a statement about the structure of the equations right now. And there is another consequence that almost nobody talks about, one that Roger Penrose has championed. If information is truly destroyed in black holes, it might explain why the universe has an arrow of time. Penrose argued that gravity is special, that gravitational collapse is the one process in nature that is genuinely irreversible at a fundamental level, and that this irreversibility is what distinguishes past from future. If black holes destroy information, the second law of thermodynamics is not merely a statistical tendency. It is a hard law, enforced by gravity. The universe does not just tend toward disorder. It is required to. Your memories of the past exist, but your memories of the future do not. And Penrose would say that is because gravity makes the past genuinely different from the future, not just statistically different. This is a minority position, but it is held by a Nobel laureate and it connects the information paradox to the deepest question in all of physics, which is why time has a direction. And it was into this silence, this collective refusal to confront the problem head-on, that two physicists walked in from opposite directions and arrived at the same conclusion. Information cannot be destroyed. Hawking must be wrong. And they were both willing to spend decades fighting about it. Leonard Susskind was born on June 16, 1940, in the South Bronx. His family was working-class Jewish. His father was a plumber. When his father became ill, 16-year-old Susskind took over the plumbing work to support the family. When he told his father he wanted to become a physicist, his father misheard pharmacist and protested. Then his father poked him in the chest with a piece of plumbing pipe and said, "You are not going to be an engineer. You are going to be Einstein." He earned his bachelor's degree from City College of New York in 1962 and his doctorate from Cornell in 1965. Along with Yoichiro Nambu and Holger Beck-Nielsen, he independently discovered around 1970 that the Veneziano dual resonance model could be described by vibrating strings, making him one of the founders of string theory. He is now the Felix Bloch Professor of Physics at Stanford. In 1981, at a conference in San Francisco, Susskind heard Hawking present his argument that information is destroyed in black holes. He later described his reaction as intense physical discomfort. He became, by his own account, intensely upset. Not because he thought Hawking was being provocative, because he understood immediately what information loss would mean for the foundations of quantum mechanics. 3 years later, in 1984, Susskind published a paper with Thomas Banks and Michael Peskin that made the consequences concrete. If information is genuinely lost in black holes, they calculated the vacuum temperature of the universe should be approximately 10 to the 32nd power Kelvin. That is a temperature so absurdly high that its existence would make organized matter impossible. Stars could not form. Atoms could not exist. You could not exist. The fact that you do exist, that the vacuum is cold and stable, is evidence that information loss does not happen. But the paper could not explain how information survives, only that it must. Gerard Hooft arrived at the same conclusion from a completely different direction. Born on July 5, 1946, in Den Helder, Netherlands, Hooft came from scientific aristocracy. His great-uncle was Fritz Zernike, winner of the 1953 Nobel Prize in Physics. His uncle, Nico van Kampen, was a prominent theoretical physicist. Tood Hooft earned his doctorate from Utrecht University in 1972, proving that Yang-Mills gauge theories are renormalizable, which provided the mathematical foundation of the standard model of particle physics. He shared the 1999 Nobel Prize with his advisor Martinus Veltman. But there is a piece of 't Hooft's story that carries a particular sting. In 1972, the same year he completed his doctorate, 't Hooft also discovered asymptotic freedom, the property that the strong nuclear force becomes weaker at shorter distances. He worked it out. He had the result, and he did not publish it. The following year, David Politzer, David Gross, and Frank Wilczek independently discovered the same thing, published it, and received the 2004 Nobel Prize for it. Hooft watched someone else win the Nobel for a discovery he had made first. He learned the hard way what it costs to stay silent when you know something is true. When he encountered Hawking's claim about information loss, his response carried the force of that lesson. Non-unitary evolution is impossible, he said. A black hole is just like other objects, like a bucket of water. So the stage was set for what Susskind would later call the Black Hole War. On one side, Hawking and Kit Thorne, arguing that information is genuinely destroyed and that quantum mechanics needs to be modified. On the other side, Susskind and Hooft, arguing that information is preserved and that something about our understanding of black holes is wrong. The stakes were not abstract. They were about whether the framework that describes every atom, every molecule, every interaction in the universe is fundamentally correct or fundamentally broken, and neither side could prove their case. Because to settle the argument, you would need a theory of quantum gravity, a complete theory that unifies quantum mechanics and general relativity. No such theory existed. The argument was about what the right answer must be, not about what the right answer is. Both sides had ironclad logic. Both sides had mathematical backing, and the two positions were mutually exclusive. For 12 years, the debate burned without resolution. Then, in June 1993, Susskind proposed something radical, a way to have it both ways, an idea he developed with Lars Thorlacius and John Uglum at Stanford, published in Physical Review D, Volume 48, Number 8, pages 3,743 through 3,661. They called it black hole complementarity. The idea was this: information that falls into a black hole is both reflected at the event horizon and passes through it. An observer watching from the outside sees infalling matter absorbed by a hot membrane called the stretched horizon, located 1 Planck length above the event horizon. 1 Planck length is about 1.6 times 10 to the negative 35th meters, which is about 10 to the negative 20th the size of a proton. This is not a physical membrane in the ordinary sense. It is a quantum mechanical description. In this picture, the stretched horizon scrambles in falling information across its surface and gradually re-emits it as Hawking radiation, in much the same way that a hot coal absorbs energy and re-radiates it as thermal photons that nonetheless carry correlations encoding what the coal is made of. The outside observer concludes that information is preserved. Meanwhile, an observer falling into the black hole crosses the horizon and notices nothing special. No membrane, no scrambling. Just smooth space-time, exactly as general relativity predicts. The equivalence principle holds perfectly. The infalling observer does not burn, does not encounter any barrier, does not notice anything unusual. They simply fall through. Both descriptions are valid. Both are complete. And the key insight was that no single observer can ever confirm both. The outside observer cannot cross the horizon to check what happened to the infalling observer, because once you cross, you cannot send information back out. The infalling observer cannot send a message back to the outside observer confirming that the horizon was smooth, because the message would have to travel faster than light to escape. Since the two descriptions can never be compared by any physical experiment, no contradiction arises. It is like a cosmic version of quantum mechanics' wave-particle duality, elevated from the microscale to the scale of space-time itself. There was a subtle reason this worked, and it relied on a result from quantum information theory. The no-cloning theorem says you cannot make an exact copy of an arbitrary quantum state. If the outside observer sees information reflected at the stretched horizon, and the infalling observer sees the same information pass through, that sounds like cloning. Two copies of the same information existing simultaneously. Complementarity evades this by arguing that the two copies are never accessible to the same observer. You can have a copy outside and a copy inside, But since no physical process can compare them, the no-cloning theorem is not violated. The information exists in one place or the other, depending on who asks, but never in both at once, from any single perspective. This was elegant. This was reassuring. And for nearly 20 years, most of the physics community accepted it. The paradox appeared to be resolved, or at least contained. The black hole war seemed to be winding down, with a negotiated settlement that let both sides claim partial victory. But there was a problem buried in the foundations of complementarity that nobody recognized for 19 years. And in the summer of 2012, 4 physicists in Santa Barbara found it. And when they published what they found, it did not just challenge complementarity, it demolished it. And it reopened the information paradox in a form that was worse than anything Hawking had originally imagined. On February 6, 1997, 3 physicists met in Pasadena, California, and signed a bet. Stephen Hawking affixed his thumbprint because his ALS made a written signature impossible. Kip Thorne wrote out the wager in his own handwriting. John Preskill, a quantum information theorist at Caltech, stood on the other side. The document read, in part, that Hawking and Thorne firmly believed information swallowed by a black hole is forever hidden from the outside universe and can never be revealed even as the black hole evaporates and completely disappears. Preskill firmly believed that a mechanism for the information to be released must and will be found. The stakes were an encyclopedia of the winner's choice, from which information can be recovered at will. The phrasing was deliberate. The encyclopedia was the physical embodiment of the argument. Information, recoverable or not. For 7 years, the bet stood unresolved. Then, on July 21, 2004, at the 17th International Conference on General Relativity and Gravitation in Dublin, Ireland, Hawking called a press conference. The room was packed. News cameras lined the walls. Hawking had teased the announcement in advance, saying he had solved the information paradox. He had changed his mind. After 30 years of defending information loss, he was conceding the bet. The atmosphere was electric. Many physicists in the audience expected a genuine breakthrough. What they got was something more complicated. Hawking presented a calculation using Euclidean path integrals, arguing that a true event horizon never forms, only an apparent horizon. The distinction is technical but important. A true event horizon is a global feature of spacetime, defined by the complete future history of the universe. An apparent horizon is a local feature, defined by the behavior of light rays at a specific moment. Hawking argued that if only apparent horizons form, then information can in principle leak out as the apparent horizon fluctuates. The black hole is not a perfect trap. It is a very good trap with tiny, temporary exits. He presented Preskill with a copy of Total Baseball, the Ultimate Baseball Encyclopedia, which had been specially flown from the United States. Hawking's quip was characteristically dry. I gave John an encyclopedia of baseball, but maybe I should just have given him the ashes. The joke was pointed. Burning an encyclopedia destroys the physical book, but not the information, because the ash and smoke and heat still encode the original data. That was exactly the point. Information survives even radical transformations. But the concession was less than it appeared. The physics community was almost entirely unconvinced by Hawking's specific calculation. Many felt he had changed his conclusion without changing the argument. The Euclidean path integral approach he used was mathematically suspect in the relevant regime, and the claim about apparent horizons versus true horizons did not obviously resolve the paradox. Preskill accepted the encyclopedia, but explicitly declined to agree with Hawking's reasoning. He said publicly that the loser conceded, but he was not sure the loser understood why he had lost. Kip Thorne did not concede at all. He said only that he thought Stephen was very likely right, but he was not willing to say so definitively. The Dublin press conference became famous. It was covered by every major newspaper, BBC, CNN, the New York Times, and the coverage uniformly presented it as the resolution of a great mystery. Hawking concedes. Information is preserved. Mystery solved. But the physicists in the room knew better. Several told reporters off the record that they did not think Hawking's argument worked. The conference organizers had scheduled the press conference before the talk, which was unusual and signaled skepticism. And in the weeks that followed, as the physics community digested the actual calculation, the consensus was clear. Hawking had joined the right side. He had not brought the right proof. And here is the part that almost never gets reported. Hawking's concession changed nothing about the actual physics. He changed his position. He did not change the equations. He offered no mechanism by which information actually escapes a black hole. He did not explain what is wrong with his original calculation. He simply decided that quantum mechanics was probably right, and general relativity must somehow accommodate it. That is a statement of faith, not a proof. The information paradox remained exactly as unsolved the day after Dublin as it was the day before. The press coverage made it sound like the mystery was closed. It was not even close. Hawking continued working on the problem until his death. In 2016, he collaborated with Malcolm Perry of Cambridge and Andrew Strominger of Harvard on a proposal involving soft hair, a term for zero-energy quantum excitations on the event horizon that might store information about infalling matter. The idea was that even though the no-hair theorem says black holes are described by only mass, charge, and angular momentum, there are additional zero-energy degrees of freedom, soft photons and soft gravitons, that can live on the horizon and carry information. Hawking presented this at a conference in Stockholm in August 2015, saying that the information is not stored in the interior of the black hole as one might expect, but on its boundary, the event horizon. The proposal generated attention, but remained incomplete at the time of Hawking's death. It was not clear that soft hair could carry enough information to account for the full Beckenstein-Hawking entropy, and the mechanism for transferring interior information to the horizon was not specified. It was, like so many proposals in this field, a direction rather than a destination. But the real reason the paradox did not end with Hawking's concession in Dublin was something that had happened 7 years earlier, in 1997, and that changed the entire landscape of the debate without immediately resolving anything. On November 27, 1997, a young Argentinian physicist at Harvard named Juan Malda Sena posted a paper to the arXiv that would become the most cited paper in the history of high-energy physics. The paper proposed a specific mathematical duality between a theory of quantum gravity in a particular kind of curved spacetime, called anti-de Sitter space, and a quantum field theory without gravity living on the boundary of that spacetime. This was the ADS/CFT correspondence, and it provided, for the first time, a concrete framework in which the holographic principle was not a conjecture, but a proven mathematical equivalence. The boundary theory is manifestly unitary. It preserves information by construction. It is just ordinary quantum field theory, living on the boundary, obeying all the usual rules. And if the boundary theory is equivalent to the bulk gravitational theory, then the bulk theory must also preserve information. Black holes in the interior must evaporate unitarily. Information must escape. Hawking must be wrong, not because of a clever argument or an appeal to consistency, but because the boundary theory says so, and the boundary theory is exact. This was a landmark result, but it had a frustrating limitation. ADS/CFT tells you that information is preserved. It does not tell you how. The boundary theory has no event horizons, no Hawking radiation, no obvious analog of a black hole interior. It describes the same physics in a completely different language. Asking ADS/CFT how information escapes a black hole is like asking a Chinese translation of a Russian novel where the characters in Moscow are. The information is there, encoded in the translation, but it does not map onto the original geography in any obvious way. So, by 2012, when AMPS published the Firewall paper, the state of the field was this. ADS/CFT strongly suggested information is preserved. Hawking had conceded, though his concession was unconvincing. Complementarity was the consensus resolution, but nobody had actually shown, using gravitational physics, that information escapes. Nobody had derived the page curve. Nobody had found the mechanism. And then AMPS showed that complementarity does not work, and the paradox was not just reopened. It was worse than ever, because now the community knew information must be preserved, thanks to ADS/CFT, but every proposed mechanism for preserving it had been demolished. The real blow was not that the firewall paradox was discovered. The real blow was that it was discovered in a regime that should have been safe. The AMPS argument does not rely on Planck scale physics. It does not require exotic quantum gravity effects. It uses standard quantum field theory and standard quantum information theory applied to regions of space-time where gravity is weak and all the usual rules should apply. The contradiction is not hidden behind the singularity, where everyone expects physics to break down. It is right at the event horizon, in mild curvature, where both general relativity and quantum mechanics should work perfectly. That is why the paradox is so lethal. The conflict is not at the edge of physics. It is in the heart of the territory that both theories claim to describe accurately. The real blow was still coming, because Suskin's complementarity, the idea that had calmed the field for nearly 2 decades, rested on a specific assumption. It assumed that the two descriptions of the event horizon, the hot membrane seen by the outside observer and the smooth space-time experienced by the infalling observer, could never be compared. It assumed that no experiment could ever reveal a contradiction between them. And in July 2012, 4 physicists showed that this assumption is wrong. Not wrong in a subtle, technical, arguable way. Wrong in a way that forces you to accept one of 3 conclusions, each of which is devastating. In October 1993, Hooft had published a paper with a title that sounded like mathematics and turned out to be prophecy: Dimensional Reduction in Quantum Gravity, posted to the arXiv as Gray QC 931026. In it, he proposed that at the Planck scale, the observable degrees of freedom in any region of space are best described not as a 3-dimensional volume, but as Boolean variables on a 2-dimensional lattice. The number of fundamental degrees of freedom, he argued, scales with area, not volume. In 1995, Susskind gave this a precise mathematical formulation in The World as a Hologram, published in the Journal of Mathematical Physics, Volume 36, pages 6377 through 6396. Between them, they had named the holographic principle, the idea that the information content of any region of space is encoded on its boundary surface, like a hologram projecting a three-dimensional image from a two-dimensional film. At the time, this sounded abstract, speculative, the kind of idea that theorists entertain without expecting it to become real. But it kept coming back. Beckenstein's entropy formula said the information in a black hole is proportional to its area. Hooft's dimensional reduction said the fundamental degrees of freedom of any region scale with area. Suskin's holographic principle said information is encoded on boundaries, the same pattern appearing independently from different calculations, all pointing in the same direction. The information in a volume of space is not proportional to the volume. It is proportional to the surface area enclosing it. You have been told your whole life that you live in 3 spatial dimensions, that the space you occupy has depth, that the room you are sitting in has volume, that the distance between you and the wall behind you is a real physical fundamental thing. The holographic principle says that might not be true. It says the fundamental description of reality might be two-dimensional, and the three-dimensional world you experience might be a projection, not a metaphor, not an analogy, a mathematical statement about the structure of physical law. But in 2004, that was still in the future. The physics community was focused on complementarity, which seemed to work, and Hawking's concession, which seemed to close the book. The holographic principle was interesting, but seemed disconnected from the practical question of how information escapes a black hole. Then, July 2012 happened, and every comfortable assumption the field had been resting on for 2 decades was torn apart. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully were all at the University of California, Santa Barbara. Almheri and Sully were graduate students. Polchinski was one of the most influential string theorists alive. Marolf was a professor specializing in gravity and quantum information. On July 13, 2012, they submitted a paper to the Arxiv with the title Black Holes, Complementarity, or Firewalls. The Arxiv identifier is 1207.3123. It was published the following year in the Journal of High Energy Physics, JHEP 1302-062, and it hit the theoretical physics community like a detonation. Their argument used a principle from quantum information theory called monogamy of entanglement. The principle says that if a quantum system A is maximally entangled with system B, then A cannot be entangled with a third system C at the same time. This is not a suggestion, it is a mathematical theorem. Entanglement is a finite resource, and maximal entanglement is exclusive. Now apply this to a black hole that has been evaporating for a long time. Specifically, consider a black hole past its page time, the point at which it has emitted roughly half its initial entropy. Don Page had calculated in 1993 that this is when the Hawking radiation must begin carrying information back out if unitarity is to be preserved. After the page time, new Hawking quanta emitted by the black hole must be entangled with the previously emitted radiation, because unitarity requires the total state of the radiation to gradually purify. At the same time, quantum field theory in curved spacetime requires each emitted Hawking quantum to be entangled with a partner mode behind the event horizon, because this entanglement is what maintains smooth spacetime at the horizon, which is the equivalence principle. The escaping quantum must be entangled with the old radiation to preserve unitarity, and it must simultaneously be entangled with a mode behind the horizon to preserve the equivalence principle. Monogamy of entanglement says it cannot be entangled with both. Something has to break. The AMPS paper identified 3 postulates that cannot all be simultaneously true. Postulate 1. Unitarity. Black hole evaporation preserves information. Postulate 2. Effective field theory is valid outside the stretched horizon. The standard rules of quantum field theory apply in regions of low curvature. Postulate 3. The equivalence principle holds at the horizon. An observer falling through the event horizon of a large black hole notices nothing special. Space-time is smooth there. At least one of these 3 must be false, and each option is catastrophic. If unitarity fails, quantum mechanics is broken. That is Hawking's original position, and the vacuum temperature argument shows it leads to absurdity. If effective field theory fails outside the horizon, then the rules of quantum physics break down in a region where they should work perfectly, far from any singularity, in what should be ordinary low curvature spacetime. This would mean the laws of physics are unreliable even in mild gravitational fields. If the equivalence principle fails at the horizon, then an infalling observer does not pass smoothly through the event horizon. Instead, the broken entanglement between the outgoing radiation and the interior modes releases a burst of energy at the horizon. The horizon becomes a firewall, a wall of high-energy quanta that incinerates anything that crosses it. The event horizon is not a featureless boundary. It is a furnace. And the equivalence principle, the idea on which Einstein built general relativity in 1915, is wrong. Each option dismantles something fundamental. There is no comfortable exit. Complementarity, which had been the consensus resolution for 19 years, fails because it assumed postulate 3. It assumed smooth horizons. The firewall argument showed that you cannot maintain smooth horizons and unitarity simultaneously after the page time. The negotiated piece of complementarity was built on a hidden contradiction that took 2 decades to expose. Think about option 3 for a moment, the firewall, because it is the one that most physicists find the most viscerally disturbing. General relativity's equivalence principle says that there is no local experiment that can distinguish between floating in empty space and falling through the event horizon of a sufficiently large black hole. For a black hole, the mass of a galaxy, the tidal forces at the horizon are negligible. You would not feel anything. You would not notice anything. You would sail through as smoothly as passing through an invisible doorway. Einstein built general relativity on this principle in 1915. It is the foundation on which the entire geometric theory of gravity rests. If the firewall is real, then falling into a black hole after the page time means being incinerated by a wall of Planck energy particles. The gentle passage that general relativity promises is a lie. The event horizon is not a boundary in space-time. It is a boundary of space-time. Behind it, there may be nothing. The interior of the black hole, the region that general relativity describes in meticulous mathematical detail with its inexorable infall toward the singularity, may not exist. At least, not in the way that general relativity describes it. The interior may be a description that only makes sense before the page time, when complementarity still works, and that ceases to be valid once the entanglement structure of the radiation crosses the page threshold. And the page time is not some exotic limit. For a solar mass black hole, the page time is roughly half the total evaporation time, which is around 10 to the 67th years. That is an incomprehensibly long time by human standards, but it is a finite, well-defined moment in the black hole's lifetime. After that moment, general relativity's description of the black hole interior may simply be wrong. Not approximately wrong, fundamentally wrong. The space-time geometry that general relativity computes for the interior may correspond to nothing physical. And if general relativity gives a detailed, mathematically precise description of a region that does not exist, what does that tell you about general relativity? What does that tell you about space-time? The reaction was volcanic. A major workshop convened at the Kavli Institute for Theoretical Physics in Santa Barbara in August 2013, titled Black Holes, Complementarity, Fuzz or Fire. Polchinski opened with the statement that nobody has the slightest idea what is going on. Hawking participated via Skype from Cambridge. John Preskill blogged that nearly everyone seemed confused. In their follow-up paper, now with Douglas Stanford joining as AMPSS, the authors provided a more detailed defense of the firewall argument. Joseph Polchinski's biography deserves attention here because it contains an irony that the information paradox seems to specialize in. He was born on May 16, 1954, in White Plains, New York. His father was a financial consultant of Irish descent. His mother, Joan, worked in an office. He earned his bachelor's degree from Caltech in 1975, where his freshman advisor was Kip Thorne. His doctorate came from Berkeley in 1980 under Stanley Mandelstam, and in an astonishing detail for someone who would become one of the most influential theorists of his generation. He published no papers as a graduate student. 0. He joined the Kavli Institute at Santa Barbara in 1992 and remained there for the rest of his life. In 1995, Polchinski made the discovery that secured his place in the history of physics. He showed that strings can end on higher dimensional, dynamical objects, called D-branes, published in Physical Review Letters, Volume 75, page 4724. This single insight triggered the second superstring revolution and enabled Andrew Strominger and Kumran Vafa to derive the Beckenstein-Hawking entropy formula from a microscopic counting of quantum states in 1996, providing the first concrete evidence that string theory could explain black hole thermodynamics. His 2-volume textbook, String Theory, published by Cambridge University Press in 1998, became the standard reference for a generation. He wanted to title it Joe's Big Book of String, and then came the Firewall paper in 2012. Polchinski and his collaborators had kicked over the hive and watched the bees swarm. He had sharpened the information paradox into its most lethal form. Every proposed escape route was closed. Every compromise was exposed as inconsistent. On approximately December 3rd, 2015, 3 days after giving a talk in Berlin celebrating the centennial of general relativity, Polchinski suffered a seizure. He was diagnosed with brain cancer. As treatment progressively affected his cognitive abilities, he turned to writing his scientific memoir, Memories of a Theoretical Physicist, posted to the Arxiv in August 2017. Friends described it as therapeutic. In the memoir, He wrote of the firewall paradox with something that reads like satisfaction. It was fun to have once again kicked over the hive and watched the bees swarm. He died at home in Santa Barbara on February 2nd, 2018. He was 63 years old. 6 weeks later, on March 14th, Stephen Hawking died in Cambridge. He was 76. Two of the central figures of the information paradox, gone within 6 weeks of each other. One had created the paradox. The other had proven that the leading resolution was wrong. And the breakthrough that many physicists consider the most significant progress on the paradox since Hawking's original calculation came approximately 16 months after Polchinski's death. One of its lead authors was Ahmed Al-Mehri, Polchinski's own graduate student. The man who sharpened the crisis more than anyone never saw the first light of what might be a resolution. But the resolution, when it arrived, did not do what anyone expected. It did not explain how information escapes a black hole. It did not choose between the three postulates. Instead, it did something far stranger. It derived the right answer from the wrong theory. And in doing so, it revealed something about the structure of space-time that was more unsettling than the paradox itself. The years between the Firewall paper and the 2019 breakthrough were a period of intense, often confused activity. Hundreds of papers were written proposing ways around the firewall argument. Daniel Harlow and Patrick Hayden proposed in 2013 that the quantum computation needed to verify the entanglement between old and new Hawking radiation would take an exponentially long time, longer than the black hole's evaporation, meaning the AMPS thought experiment could never actually be performed. This was called computational complexity as a physical constraint, and it suggested that the laws of physics might protect their own consistency by making certain operations computationally impossible. It was a novel idea, but it left many physicists uneasy. The idea that physics protects itself through computational difficulty felt more like an escape clause than an explanation. Others proposed radical modifications. Papadodimas and Raju at CERN suggested that the interior operators of a black hole depend on the state of the radiation, a form of state dependence that troubled many physicists because it seemed to undermine the standard framework of quantum mechanics. Nomura, Varela, and Weinberg explored a multiverse interpretation in which different branches of the wave function see different black hole interiors. Valinda and Valinda proposed that the entanglement structure of space-time itself breaks down near old black holes. Each proposal had defenders. None achieved consensus. Meanwhile, Malda Sena and Suskin's ER equals EPR conjecture, published in the summer of 2013, offered a geometric language for thinking about the problem. If entanglement is geometry, then the entanglement between old Hawking radiation and the black hole interior is a wormhole connecting them. The infalling observer passes through the horizon, but the interior they enter is the same interior that the radiation describes from the outside. There is no cloning, because inside and outside are connected. There is no firewall, because the entanglement has a geometric realization that smooths the horizon. The proposal was beautiful and deeply intuitive, but it remained a conjecture. Nobody could derive it from first principles. Nobody could show precisely how the wormhole avoids the AMPS argument. And so the field entered 2019 in a state of productive confusion. Everyone agreed information must be preserved thanks to ADS/CFT. Nobody could show how. The firewall argument had closed the old escape routes. The new proposals were intriguing, but unproven. What was needed was not a new idea, but a new calculation. Something that would reproduce the page curve from the gravitational side using the same mathematical tools that Hawking had used, without assuming the answer in advance. To understand what happened next, you need to understand a curve, specifically a curve drawn by a quiet, deeply religious physicist who was the first person to realize that Hawking was wrong and who waited 26 years for the rest of the field to catch up. Don Nelson Page was born on December 31st, 1948. He earned his doctorate from Caltech in 1976 under Stephen Hawking, who was visiting from Cambridge. He went on to become a professor at the University of Alberta, a fellow of the Royal Society of Canada, and a devout evangelical Christian, which made him an unusual figure in theoretical physics. His faith and his physics coexisted without apparent friction, though he once wrote a paper analyzing the probability that God exists. As early as 1980, Page published "Is Black Hole Evaporation Predictable?" in Physical Review Letters, Volume 44, page 301, arguing that information loss violates CPT symmetry. This was years before Suskin or Hooft took up the cause. Page was the first serious dissenter, and he was Hawking's own student. Then, in 1993, Page published 2 papers that would define the benchmark for the entire field for the next 3 decades. The first, Average Entropy of a Subsystem, appeared in Physical Review Letters, Volume 71, page 1291, submitted to the arXiv as Gray QC 9305-007. The second, Information in Black Hole Radiation, appeared in Physical Review Letters, Volume 71, pages 3743 through 3746. arXiv Hepth 9306-083. The argument was elegant and devastating. Consider a black hole as a quantum system, entangled with the radiation it has emitted. If evaporation is unitary, the total state of the system, black hole plus radiation, remains a pure state at all times. Now track the entanglement entropy of the radiation subsystem. Early in the evaporation, each emitted quantum is entangled with the black hole interior. The radiation's entropy increases with each emission. The radiation looks thermal, random, information-free. This continues until the black hole has lost approximately half its initial entropy, a moment Page called the Page time, which occurs roughly 53 to 54% of the way through the total evaporation. After the Page time, something changes. The radiation becomes increasingly entangled with itself rather than with the shrinking black hole. Its entropy begins to decrease. New quanta carry correlations with previously emitted radiation, and information starts to emerge. When evaporation is complete, the radiation's entropy returns to zero. It is a pure state. Information is preserved. Plot this on a graph. The entanglement entropy rises, peaks at the Page time, and falls back to zero. That is the Page curve. It has a distinctive shape, like a mountain peak, and it became the gold standard for any proposed resolution of the information paradox. Any theory that claims to preserve unitarity in black hole evaporation must reproduce the Page curve. If your calculation gives monotonically increasing entropy, as Hawking's original calculation does, you have not saved information. If it reproduces the Page curve, you might have. The importance of the Page curve cannot be overstated. It turned a philosophical argument about whether information is preserved into a quantitative test. It gave the field a target. Before Page, the debate was about principles. After Page, the debate was about a specific mathematical function that any correct theory must produce. It was like having the answer key to an exam without knowing how to solve the problems. You know what the right answer looks like. You just cannot get there. And the Page curve contains a subtle but devastating implication. If the entropy of the radiation decreases after the Page time, that means the radiation must carry subtle quantum correlations that encode information about the black hole's interior. But these correlations cannot be detected by any local measurement of individual Hawking quanta. Each individual photon or graviton in the Hawking radiation looks perfectly thermal. The information is encoded in the collective correlations between quanta emitted at different times, potentially separated by billions of years of emission. It is like trying to read a message written across 1,000,000 separate grains of sand scattered across a beach. Each grain looks random. The message is in the pattern. And detecting that pattern requires gathering essentially all of the radiation and performing a quantum computation of extraordinary complexity. The information is there. It is just as inaccessible, in practice, as if it had been destroyed. For 26 years, nobody could derive the Page curve from any calculation involving gravity. Page had described what the answer must look like if unitarity holds, but he could not prove from gravitational physics that unitarity holds. The curve was a prediction, not a derivation. It was an act of faith in quantum mechanics, backed by mathematical consistency arguments, but without a gravitational proof. Then, in May 2019, two groups independently derived it. Jeffrey Pennington, then at Stanford and Berkeley, submitted Entanglement, Wedge Reconstruction, and the Information Paradox to the arXiv on May 20th, 2019. It was published in the Journal of High Energy Physics in September 2020. One day later, on May 21st, Ahmed Almhiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield submitted the Entropy of Bulk Quantum Fields and the Entanglement Wedge of an Evaporating Black Hole, published in JHEP in December 2019. Both papers built on the quantum extremal surface prescription proposed by Engelhardt and Aaron Wall in 2014. The breakthrough introduced what became known as the island formula. The formula computes the entanglement entropy of the Hawking radiation using a new rule. In addition to the expected contributions from the radiation itself, you must also consider the possibility that a region of spacetime inside or near the black hole, called an island, contributes to the radiation's entropy even though it is geometrically disconnected from the radiation region. The entropy is the minimum over all possible extremal surfaces of the sum of the area of the surface, divided by 4 times Newton's constant, plus the bulk entropy of quantum fields in both the radiation region and the island. Before the Page time, the trivial option with no island gives the lowest entropy. The radiation entropy increases monotonically, exactly as Hawking calculated. The radiation looks thermal. No information escapes. This matches the rising part of the Page curve. After the Page time, a new option appears. A non-trivial island located just inside the event horizon gives a lower total entropy than the no island option. The island's contribution means that interior degrees of freedom are now counted as part of the radiation's quantum description. The entropy starts to decrease. Information begins to emerge. When the evaporation is complete, the entropy returns to 0. The Page curve is reproduced. Think about what that means for a moment. a region of space-time inside the black hole, behind the event horizon, in a place where nothing is supposed to escape, is mathematically owned by the radiation outside. The information is not smuggled out through some physical process. The boundary between inside the black hole and outside the black hole is redrawn by the mathematics. The universe at the level of quantum information does not respect the geometric boundaries that general relativity imposes. Space-time is not the final word on what belongs where. Information is. In November 2019, 2 more papers extended the result using replica wormholes, a technique from the gravitational path integral. Pennington, along with Stephen Schenker, Douglas Stanford, and Zhenbin Yang, and separately Almheri, Thomas Hartmann, Juan Malda Sena, Edgar Chagolian, and Amir Hossein Tajdini showed that when you compute the entanglement entropy using the gravitational path integral, new saddle point geometries appear. These are space-time wormholes that connect different replica copies of the system. Before the page time, the disconnected saddle dominates. After the page time, the connected saddle, the one with wormholes, dominates. The wormholes are not optional features of the calculation. They are demanded by the mathematics of the path integral. The gravitational path integral requires these wormhole contributions to produce a unitary answer. This connected directly to a conjecture that Malda Sena and Suskin had proposed in June 2013, in the immediate aftermath of the Firewall crisis. Their paper, Cool Horizons for Entangled Black Holes, ArcSIF 1306.0533, proposed an idea captured in the equation ER equals EPR, Einstein-Rosen bridges, which are wormholes, and Einstein-Podolsky-Rosen correlations, which are quantum entangled. They are connected by a wormhole. When the Hawking radiation is entangled with the black hole interior, that entanglement is a geometric connection, a bridge through space-time, linking regions that appear disconnected. Susskind recalled that one day Malda Sena sent him a very cryptic message containing the equation ER equals EPR. He said he instantly saw what Malda Sena was getting at. If ER equals EPR is correct, it means the island formula is not just a mathematical trick. It is a statement about the geometry of space-time. The radiation and the interior are connected by wormholes. The information is not lost because the boundary between inside and outside is not what you thought it was. Space itself is woven from entanglement. Cut the entanglement and space tears apart. Establish new entanglement and new connections form. The geometry of the universe is not fixed. It is emergent. It reorganizes itself based on quantum correlations. Mark van Ramsdonk, a physicist at the University of British Columbia, made this idea vivid in a 2010 paper that was initially rejected by a major journal for being too speculative, and then went on to become one of the most influential papers in the field. He considered a quantum system in a specific entangled state called the thermofield double, which in the AD/CFT correspondence describes 2 black holes connected by a wormhole. Then he asked, what happens if you gradually reduce the entanglement between the 2 halves of the system? The answer, derived from the AD/CFT dictionary, was that the wormhole stretches and thins. Reduce the entanglement further, and the wormhole pinches off. The 2 sides of space-time disconnect entirely. The geometric connection between 2 regions of space is literally made of entanglement. Remove the entanglement, and you do not get two regions of space with nothing between them. You get two regions of space with no between at all. The space between them ceases to exist. This is not an analogy. This is a derivation within ADS/CFT. Van Ramstonk concluded that entanglement is the fabric of space-time, that it is the mechanism by which disconnected points become geometrically related. Space does not exist first, with quantum fields living inside it. Quantum entanglement exists first, and space is the emergent description of what entanglement looks like at large scales. If this is right, and the evidence from multiple independent lines of research suggests it is, then every spatial relationship you experience, the distance between your hand and your face, the depth of the hallway outside your door, the light years between here and Alpha Centauri, is a manifestation of quantum entanglement between underlying degrees of freedom that do not themselves live in space. They are more fundamental than space. Space is what they produce. The intellectual foundation for much of this was laid by Juan Malda Sena's 1997 conjecture of the ADS/CFT correspondence. Malda Sena, born on September 10, 1968, in Buenos Aires, Argentina, now at the Institute for Advanced Study in Princeton, proposed an exact mathematical duality between quantum gravity and anti-de Sitter space, a space-time with negative cosmological constant, and a conformal field theory living on its boundary. This was the first concrete realization of the holographic principle, because the boundary theory is manifestly unitary, meaning it preserves information by construction. Any process in the bulk spacetime, including black hole formation and evaporation, must also preserve information. It is the strongest theoretical evidence that Hawking was wrong, and it is, to this day, the most cited paper in high-energy physics, with over 10,000 citations. By the mid-2000s, ADS/CFT had shifted the balance of opinion in the field decisively toward unitarity. The question was no longer whether information is preserved. For most physicists, the question was how, and that question remains unanswered. But here is what should disturb you about the 2019 breakthrough. It derived the right answer. The page curve is reproduced. Information appears to be preserved, and nobody understands why it works. Raphael Bousseau, a physicist at Berkeley, put it bluntly: "We now can compute the page curve, and I do not know why." Pennington expressed a similar frustration. The hope was that in order to answer this question, they would have had to learn about the microscopic theory of quantum gravity. Instead, they found that ordinary semi-classical gravity, the same framework Hawking used, was sufficient to get the right answer. You did not need string theory. You did not need quantum gravity. You just needed to include the island contribution that Hawking had missed. The calculation that produces the crisis also produces the resolution, if you do it correctly. And the fact that it was so easy that you did not need fundamentally new physics was in some ways more disturbing than the paradox itself, because it meant the field might not learn as much from the resolution as they had hoped. Tom Hartman, a physicist at Cornell, offered a measured assessment. It solves some corner of the paradox. Some corner. After 50 years, the mathematics shows that information escapes. The mathematics does not show how. The mechanism remains unknown. The island formula tells you the answer is unitary. It does not tell you what happens to a specific quantum of information when it crosses the event horizon. It does not resolve the firewall paradox. It does not tell you whether an infalling observer hits a wall of fire or falls through smoothly. It does not explain what the interior of a black hole is made of. It calculates the right entropy curve without explaining the physics that produces it. It is an answer without a story, a destination without a path. And the limitations go further. The original calculations were performed in two-dimensional Jackie White-Teitelbaum gravity, a toy model that captures some features of real black holes, but is not four-dimensional spacetime. The applicability to actual black holes in our universe, which has a positive cosmological constant rather than the negative one of anti-de Sitter space, is not fully established. A 2021 paper showed that the island formula fails entirely for certain two-dimensional Liouville black holes, suggesting it may not be universal. And the replica wormhole calculation carries a deeply troubling implication. The gravitational path integral, when it includes wormholes, appears to describe not a single theory of quantum gravity, but an ensemble average over many possible theories. This is the factorization puzzle, and it remains unresolved. If the path integral describes an average, then the specific theory that describes our universe is only one member of the ensemble, and the Page curve is only correct on average, not for any particular black hole. Nobody knows if that is a feature or a problem. So the most celebrated breakthrough in the information paradox in decades showed that information is preserved, could not explain how, and may not even apply to the actual universe. And the reason physicists are still excited about it, the reason it generated hundreds of follow-up papers and multiple conference series, is not because it solved the paradox. It is because of what it revealed about the nature of space-time, something that Hooft glimpsed in 1993, that Suskin formalized in 1995, that Malda Sena proved in a specific context in 1997, and that the island formula made unavoidable in 2019. The information content of any region of space is proportional to the area of its boundary, not its volume, its area. And this is where the information paradox stops being about black holes and starts being about you. Beckenstein's entropy formula says the maximum information inside a black hole is proportional to the area of its event horizon. The Beckenstein bound, which he derived separately, says the maximum information in any region of space, not just inside black holes, is bounded by 2 pi KRE over h bar c, where r is the enclosing radius and e is the total energy. That formula contains no gravitational constant. It applies everywhere. It applies to the room you are in right now. The maximum information content of any sphere in space is proportional to the sphere's surface area, not its volume. The holographic principle generalizes this. The fundamental degrees of freedom of any region of space are encoded on its boundary surface. The three-dimensional interior is, in some deep sense, a projection of that two-dimensional boundary. This is not a conjecture anymore. In the context of ADS/CFT, it is a proven mathematical duality. A lower dimensional theory without gravity on the boundary is exactly equivalent to a higher dimensional theory with gravity in the interior. The interior emerges from the boundary. Depth is not fundamental. It is derived. The island formula reinforces this. It shows that the quantum information in a black hole's interior can be owned by a system on the outside, because the boundary between inside and outside is not fixed by geometry. It is determined by quantum information. Space-time is not the container that holds information. Information is the substrate from which space-time is constructed. The ER equals EPR conjecture takes this further. If entanglement and geometry are the same thing, then the spatial connections you experience the distances between objects, the continuity of space from one point to another, are all consequences of quantum entanglement between underlying degrees of freedom. Space does not exist first, with entanglement happening inside it. Entanglement exists first, and space is what it looks like from the inside. Mark van Ramsdonk, whose thought experiments inspired the ER equals EPR conjecture, demonstrated that if you systematically remove entanglement between two halves of a quantum system, the geometric space connecting them tears apart. Entanglement is the thread that sews space-time together. Without it, there is no space, and the three-dimensional depth you experience, the sense that you're inside a room, that there is volume around you, that the world extends in three spatial directions, may be a story your brain tells you about information that is actually encoded on a distant two-dimensional surface. This is not a metaphor. This is not an analogy. This is what the mathematical structure of the only consistent quantum gravity framework we possess actually says. The holographic principle, proven in the context of ADS/CFT. The Beckenstein bound, which applies universally. The island formula, which shows that geometric boundaries are not information theoretic boundaries. ER equals EPR, which identifies geometry with entanglement. All of them point in the same direction. Three-dimensional space may not be real. It may be emergent. Consider what this means concretely. The Beckenstein bound says the maximum information in a sphere 1 meter in radius, containing 1 kilogram of matter, is approximately 2.5 times 10 to the 43 bits. That number depends on the radius and the energy, both of which are properties of the boundary, not the interior. If you want to know the maximum number of distinguishable quantum states that can fit inside that sphere, you look at the surface, not the volume. This is wildly counterintuitive. In everyday experience, the amount of stuff you can fit in a box depends on its volume. A bigger box holds more. But the Beckenstein bound says the maximum information scales with the surface area, which grows as the square of the radius, not the cube. A sphere 10 times wider has 100 times more maximum information, not 1,000 times. The extra information you think should fit in the extra volume is not there. It cannot exist. The bound forbids it. And this is not a bound derived from black hole physics and then extended by analogy. The Beckenstein bound contains no gravitational constant. It is a result from quantum field theory and special relativity alone. It applies in flat space-time. It applies in a laboratory on Earth. It applies to the hard drive you store your files on. There is less room in the universe than you think, and the room that exists is on surfaces, not in volumes. The physicists who work on this are careful about how far they push the interpretation. Many will tell you that the holographic principle is established only in the context of ADS/CFT, which describes a universe with a negative cosmological constant, and that our universe has a positive cosmological constant, so the results may not apply directly. This is true. It is also true that every time physicists have tried to extend holographic ideas beyond ADS/CFT, the extension has worked. The island formula was originally derived in ADS settings, but has since been applied with apparent success to cosmological horizons and de Sitter space. The Beckenstein bound applies universally. The pattern is consistent. The caution is understandable. The evidence is accumulating. Samir Mather at Ohio State has proposed a different resolution. The Fuzzball program, in which the classical black hole interior is replaced entirely by a quantum state, a fuzzball made of stringy degrees of freedom that has no event horizon and no singularity. In this picture, every black hole microstate has a different internal geometry, and what we call the event horizon is actually the outer boundary of this quantum fuzz. The fuzzball radiates like a normal quantum system, and information is preserved straightforwardly. This is a radical proposal. It abandons the classical black hole interior, and it has the same implication as the holographic principle. The interior is not real. What you thought was the inside of a black hole is actually a quantum structure that lives at the boundary. The competing approaches, the island formula, fuzzballs, ER equals EPR, quantum error correction, all disagree on the details. They disagree on what replaces the classical interior, on whether the firewall is real, on the role of wormholes, on the nature of the encoding. But they agree on one thing: the three-dimensional interior of a black hole is not what it appears to be. It is either emergent, or encoded on the horizon, or connected to the exterior through wormholes, or entirely absent. And if the interior of a black hole is not a genuine three-dimensional region, what makes you so confident that the interior of anything else is? Beckenstein was the first person to see this in 1973, when he proposed that a black hole's information is proportional to its area. He did not understand the full implications. Nobody did. He received the Wolf Prize in Physics in 2012 and the APS Einstein Prize in 2015. The citation for the Einstein Prize read, "For his groundbreaking work on black hole entropy, which launched the field of black hole thermodynamics and transformed the long effort to unify quantum mechanics and gravitation." Months later, on August 16, 2015, Jacob Bekenstein died unexpectedly in Helsinki, Finland. At age 68, he had traveled there to give a physics lecture. Lee Smolin called his discovery the most important in modern physics. Raphael Bousseau called him one of the very few giants in quantum gravity. He did not live to see the island formula confirm the pattern his entropy formula had first hinted at 46 years earlier. Polchinski died in February 2018. Hawking died 6 weeks later, on March 14th, the same date as Einstein's birthday. A coincidence that the universe seems to have arranged with a sense of irony. 3 of the 4 people most responsible for defining the information paradox were gone within 3 years of each other. The 4th, Leonard Susskind, turned 85 in June 2025. He is still at Stanford, he is still working, he has spent 44 years fighting a war that is not over. The information paradox is not solved. The page curve has been derived, but the mechanism by which information physically escapes a black hole remains unknown. The firewall paradox has not been resolved. Nobody knows whether an observer falling into a black hole experiences smooth space-time or a wall of fire. The island formula works in toy models, but has not been fully extended to realistic 4-dimensional black holes in a universe with positive cosmological constant. The factorization puzzle implies the gravitational path integral may not describe a single theory, and the holographic principle, for all its mathematical elegance, has not been formulated in a way that applies unambiguously to the actual universe we live in, which is not anti-de Sitter space. Researchers continue to push in multiple directions. In December 2023, Boso and Pennington showed that islands can protrude macroscopic distances outside the horizon of supermassive black holes. meaning the island is not tucked safely behind the event horizon, but extends into the region where you would be standing if you were watching from what you thought was a safe distance. The boundary between inside the black hole and outside the black hole is not where general relativity draws it. It is where the quantum information structure draws it. And the two can differ by astronomical distances. In 2024, Akers, Engelhardt, Harlow, Pennington, and Varden explored how the black hole interior is encoded through non-isometric codes and computational complexity, suggesting that reconstructing the interior from the radiation is possible in principle, but requires quantum computations so complex that no physical process in the universe can actually perform them in a reasonable time. The interior exists in this picture, but only in the way that a password exists when you know the hash but not the key. The information is there, you just cannot get to it. Loop quantum gravity researchers have begun applying island techniques to their own framework. Gravitational path integral methods are being extended to cosmological settings. A 2025 special issue of the journal Entropy collected diverse approaches including quantum hair, quantum memory matrices, and computational complexity arguments. The field is broader and more active than at any point in the 50-year history of the paradox. But it is also more fragmented. There is no consensus on which approach is most promising. There is not even consensus on what exactly was proven in 2000. Samir Mathur at Ohio State has proposed a different resolution entirely, the Fuzzball program, in which the classical black hole interior is replaced by a quantum state made of stringy degrees of freedom that has no event horizon and no singularity. In this picture, every black hole microstate has a different internal geometry, and what we call the event horizon is actually the outer boundary of this quantum fuzz. The fuzzball radiates like a normal quantum system, and information is preserved straightforwardly. This is a radical proposal. It abandons the classical black hole interior entirely, and it has the same implication as everything else. The interior is not real. What you thought was the inside of a black hole is actually a quantum structure that lives at the boundary. The competing approaches, the island formula, fuzzballs, ER equals EPR, quantum error correction, all disagree on the details. They disagree on what replaces the classical interior, on whether the firewall is real, on the role of wormholes, on the nature of the encoding. But they agree on one thing. The three-dimensional interior of a black hole is not what it appears to be. It is either emergent or encoded on the horizon, or connected to the exterior through wormholes, or entirely absent. And if the interior of a black hole is not a genuine three-dimensional region, what makes you confident that the interior of anything else is? Think about that for a moment. Black holes are not rare. There are an estimated 40 quintillion stellar mass black holes in the observable universe. Sagittarius A star, the supermassive black hole at the center of our galaxy, has a mass of about 4 million suns. The supermassive black hole in M87, the one imaged by the Event Horizon Telescope in 2019, has a mass of roughly 6.5 billion suns. Each one of these objects, according to every serious approach to the information paradox, has an interior that is not what general relativity says it is. Either the interior is holographically encoded on the horizon, or it is a fuzzball with no interior at all, or it is connected to the exterior through wormholes, or it is an emergent structure assembled from quantum information. Whatever the answer is, the classical picture of a three-dimensional region behind the horizon containing a singularity at its center is not correct. General relativity's most iconic prediction, the black hole interior, appears to be an artifact of the classical approximation, and if the interior of a black hole is an artifact, the holographic principle suggests the interior of everything else might be one too. Gerard Hooft once compared the information paradox to the ultraviolet catastrophe that led Max Planck to revise the blackbody radiation law in 1900, the revision that ultimately gave the world quantum mechanics. He said he hoped the black hole information paradox might lead to something equally great. What that something is, nobody yet knows, but the direction it points has been consistent for decades, and it has not wavered. What we have, after 50 years, is not a solution, it is a direction. Every failed attempt to solve the information paradox has pushed physics the same way, toward the conclusion that space-time is not fundamental, that geometry is emergent from quantum information, that the three-dimensional world is a holographic projection, that the interior of a black hole, the interior of a room, the interior of anything at all, may be a derived concept, not a basic one. The black hole did not create this conclusion. The black hole revealed it. The event horizon is the place where the projection fails to maintain itself, where reality stops being able to sustain the illusion of depth and interiority, where the hologram flickers. Beckenstein was the first person to see the direction in 1973 when he proposed that a black hole's information is proportional to its area. He did not understand the full implications. Nobody did. He received the Wolf Prize in Physics in 2012 and the APS Einstein Prize in 2015. The citation read, "For his groundbreaking work on black hole entropy, which launched the field of black hole thermodynamics and transformed the long effort to unify quantum mechanics and gravitation." Months later, on August 16, 2015, Jacob Bekenstein died unexpectedly in Helsinki, Finland, at age 68. He had traveled there to give a physics lecture. Lee Smolin called his discovery the most important in modern physics. Raphael Boussot called him one of the very few giants in quantum gravity. He did not live to see the island formula confirm the pattern his entropy formula had first hinted at 46 years earlier. Polchinski died in February 2018. Hawking died 6 weeks later, on March 14th, the same date as Einstein's birthday. 3 of the 4 people most responsible for defining the information paradox were gone within 3 years of each other. The 4th, Leonard Susskind, turned 85 in June 2025. He is still at Stanford. He is still working. He has spent 44 years fighting a war that is not over. There is something the information paradox does to the people who work on it. It consumes careers. Beckenstein spent his entire professional life on the thermodynamic properties of black holes and their implications for information. Hawking spent 42 years entangled with a paradox he created, switched sides once, and died without seeing resolution. Polchinski kicked over the hive and never saw the bees settle. Don Page dissented as a graduate student and waited 3 decades for his curve to be derived. Susskind fought a public war for over 4 decades, wrote a best-selling book about it, and is still fighting. The paradox is not a problem you solve and move on from. It is a problem that restructures how you think about reality. And once it has done that, you cannot go back to thinking the old way. And the deepest implication, the one that 50 years of the information paradox has been building toward, is this. The question was never really about what happens to information when it falls into a black hole. The question was about what space is made of, and the answer that keeps emerging from the mathematics, from every independent line of reasoning, from entropy formulas and extremal surfaces and wormhole calculations and holographic dualities, is that space may not be made of anything at all. It may be a projection, an emergent description, a story that quantum information tells about itself, encoded on a boundary you will never see, about a depth that does not exist. The black hole was just the first place where physics noticed the inconsistency, the first place where two theories looked at the same region of space-time and could not agree on what was inside it, not because they were getting the wrong answer, but because the question itself, what is inside, may not have the kind of answer you were expecting. The calculations have been checked. The page curve follows the path that unitarity demands. The entropy rises, peaks at the page time, and falls. Information appears to be preserved, but the price of that preservation is the dissolution of space as you understand it. The three dimensions you navigate every day, the volume you believe you occupy, the depth of the room you are sitting in, all of it encoded according to the mathematics, on a surface. And the black hole was never a mystery about where information goes. It was a message about where you are. You are not inside the universe. You are on it. And the depth you see when you look around you is not a place you can go. It is a story being told about you by something that has no use for depth. The black hole was just the first place where the story stopped making sense.